3 astronauts enter the spacecraft Soyuz TMA-16M. 2 of them are part of an unprecedented mission in the history of space exploration. The American astronaut Scott Kelly and the Russian astronaut Mikhail Krokyenko will live on the International Space Station, the ISS, for almost a year. During this year, the International Space Station will host more than 400 scientific experiments. The bodies of the 2 astronauts are part of some of these experiments. The 2 astronauts will draw blood in space, undergo a series of medical exams such as ultrasounds, and even receive the first space vaccine. The goal is to assess what happens to the human body after a year in space, in preparation for even longer space journeys. Scott Kelly personally takes part in a second series of experiments for a curious reason. There is another person in the world with the same DNA as Scott Kelly, his twin brother Mark Kelly, who is also an astronaut.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
While Scott Kelly undergoes numerous tests and has his body analyzed at a genetic level during his stay in space, the same will happen with Mark Kelly here on Earth. Comparing the bodies of the 2 brothers, one living on Earth and the other in space, will provide unique information on how the human body adapts to living away from Earth. There are 2 major questions this study aims to answer. The first is whether a year in space is a timescale equivalent to a trip to Mars. Monitoring Scott Kelly's physical and mental condition during this year can indicate how viable a mission to Mars really is. What additional safety and health measures need to be developed before such a mission? And the second question, being a bit dramatic, do astronauts go blind in space? Numerous astronauts have reported a worsening of vision after spending months on the space station. This vision damage persisted even after returning to Earth. Scott Kelly is one of the astronauts affected by this vision loss. The possibility of studying the evolution of vision in space is one of the main objectives of the twin study. So, what happens if you spend a year in space? The trip to the space station is relatively quick, just a journey of a few hours. With the first 8 minutes of this journey being a dramatic rocket launch accelerating the spacecraft from the ground into space, a few hours later, the Soyuz capsule docks with the International Space Station and the astronauts officially begin their year-long stay in space. The first days are challenging due to a number of factors. The lack of Earth's gravity causes a series of uncomfortable physiological effects. The first of these is motion sickness. Your sense of orientation depends on various pieces of information that your body collects. One of these pieces of information is what you are seeing. Another is the movement information collected by the labyrinth, a fluid-filled structure in your ear. As you move, the fluid inside your ear sways appropriately. This helps your body estimate its position, orientation, and movement. The problem occurs when 2 pieces of orientation information conflict. For example, inside a boat, the liquid in your inner ear is affected by the rocking of the boat, indicating movement, but your eyes see the boat around you as stationary. And this is conflicting information with what your ear detects. This conflict of information causes nausea, a feeling of discomfort, and even regurgitation. And basically the same thing happens in space. Without gravity, the fluid responsible for the sense of balance floats freely, indicating movement. And all this while your eyes see the ISS as stationary, indicating that you are still. This conflict of information causes nausea in most astronauts until they get used to it. Another effect of the lack of gravity is growth. Your spine is constantly being compressed by the weight of your body. When gravity is removed from the equation, your spine relaxes and expands. Astronauts grow an average of 5 centimeters in the first few days in space. This process causes back pain and enough discomfort that they need to be medicated to not feel so bad. Additionally, in the first 24 hours of flight, an astronaut will urinate about 1.5 to 2 liters of water. A lot, and in the process, reduce the blood volume in your body. This is a consequence of fluid redistribution in the body due to the lack of gravity, and we will get into those details more towards the end of the video. Just to be clear, there is gravity on the ISS. But since the ISS is in orbit, meaning it is constantly falling, the astronauts do not feel this gravity. In practice, Scott Kelly spent a year in free fall, and therefore he was not affected by Earth's gravity. You don't feel gravity when you're falling, you only feel it when you stop falling. And then you feel it quite a lot. After a week of back pain, urination, and vomiting, the astronauts become relatively adapted to space. The most immediately dramatic effects stop, and the longer-term effects of space begin to come into play. Pelvic fractures are one of the most common health complications among retired astronauts. And this is no coincidence. Space drains the strength from their bones. Impact and load are essential for bones to maintain their health. In Earth's gravitational field, bones are constantly dealing with the force of supporting our body. Even the smallest movement helps keep bones healthy. This is your reminder to stretch. It is a principle of our biology that the body gets rid of what it doesn't use. And if you reduce the load on your bones, they will start to become weaker. This is also a problem for people who are bedridden or immobilized for long periods of time. And it is also a problem for astronauts who do not feel the effects of gravity. If nothing is done, an astronaut loses between 1% and 2% of their bone mass per month. The exact loss depends on the bones in question. This means that an astronaut on a 2-year mission to Mars would lose around 50% of their bone mass on the round trip. The astronaut's skeleton would basically lose half of its strength. To make matters worse, this loss is never completely reversed even after they return to Earth. A similar thing happens with muscles. Without the load generated by weight, muscles exert much less effort in space and tend to atrophy as well. To counteract muscle and bone loss, astronauts have a mandatory exercise routine of 2 hours per day, 6 days a week, as part of their duties. Developing exercise machines that work in space has been one of the greatest advances in space exploration in recent decades. And thanks to space exercise equipment and an exercise routine, most of the bone and muscle loss can be mitigated. Bone and muscle loss is a problem currently solved. The only better scenario would be to develop artificial gravity. Even with exercise, muscles still undergo changes in space. In a very summarized way, our muscles have 2 types of fibers: endurance fibers and explosive fibers. In space, your body tends to switch endurance fibers for explosive fibers. Most astronauts also lose weight and muscle mass even with exercise. However, this loss is not so directly associated with the lack of gravity. Astronauts consume, on average, 30% less food than they need in space. And this is not because NASA wants to save money. Astronauts simply feel less hungry than they should in space. All astronauts continuously lose weight during their stay on the space station. The exact reason for this decrease in appetite is not yet determined, but there are some possibilities. First, food in space tastes different. The smell of food is an important part of taste. The smell of hot food is carried by convection. Hot air rises and convection depends on gravity. Without gravity, the warm air carrying the smell doesn't reach your nose as intensely, affecting how astronauts perceive tastes. Another possible cause is constipation, something that seems to significantly affect astronauts in space. Additionally, the type of dominant bacteria in the astronaut's digestive system also appears to change in space. Currently, we do not know what causes what. Perhaps constipation causes a change in diet, which causes a change in the gut microbiota. Or maybe there is some other common explanation for these effects of space on food consumption. Another thing we don't know is if the weight loss of astronauts could be compensated by them eating more. Currently, no mission has been long enough for excessive weight loss to be a danger. But on a long-duration mission, such as to Mars, this could become the case, and this is one of the many unknowns of space exploration. One of the most interesting aspects of comparing Scott Kelly with his brother Mark Kelly is that they have the same DNA, the same genetic code. It is possible to try to observe the effect of space at the level of genes and the expression of these genes in the form of the proteins they produce. To begin with, Scott Kelly's DNA was not altered in any way. What changed was the way this DNA was expressed. Basically, DNA in space seems to use different tools than it normally uses here on Earth. Were parts of Scott's DNA that remained inactive in Mark activated during his stay in space? What changes which proteins and chemicals are produced by the cells? What alters the overall chemistry of the body? For example, collagen is the main protein that forms human connective tissue, the material that lies between the cells of your body. And some changes in Scott Kelly's DNA expression were associated with an increase in collagen production and excretion. The conclusion: the types of chemicals that our body produces to keep functioning seem to change in space. However, which changes cause which effects exactly still need to be better studied. Another change was in Scott's telomeres. Telomeres are additional genetic material at the ends of DNA, like the tips of shoelaces. They are associated with the genetic age of cells because they shorten every time a cell divides. Scott's telomeres increased during his stay in space, which even led to speculative news that space reduces the effective age of astronauts. But this is probably not the case. Even on Earth, weight loss and exercise are associated with a lengthening of telomeres, and Scott was experiencing both of these things in space. So much so that the increase in telomeres was reversed soon after he returned to Earth. Another effect at the genetic level was the damage caused by radiation in space. On Earth, we are protected from the radiation coming from the Sun and the rest of the universe by our planet's magnetic field. The space station is still within Earth's magnetic field, but it receives much more radiation from space than the surface of our planet. And radiation can destroy and disrupt the DNA replication process that occurs when cells multiply. Scott Kelly received the equivalent of 10 X-ray doses of radiation per day in space. And it was possible to observe 10 times more DNA replication errors in his body than in his brother's body. And this is a direct observation of the damage that radiation has on DNA replication. This damage is likely to increase Scott's risk of developing cancer for the rest of his life. Your heart is responsible for pumping oxygenated blood throughout your body. On planet Earth, your heart has to deal with the fact that gravity exists, and it is more difficult to pump blood upwards than downwards. And to perform the task of moving the blood circulating in your legs back to the heart, it receives a little help from the muscles in your legs. Your leg veins are a bit tighter than the rest of the body, which makes it easier for your blood to flow back to the chest area. Removing gravity, this still holds true. In space, blood tends to move away from the legs and accumulate excessively around the heart and face. This leads to the so-called puffy face and bird leg syndrome. And I'm not kidding, those are the actual names. Your face becomes swollen with blood and your legs become dry and thin. It's precisely this redistribution of blood that makes the body think it has too much blood. And then it makes the astronauts urinate a lot during their first days in space. The excessive urination is the body's attempt to reduce the excessive volume of blood in circulation. And worse, the pressure inside your skull increases due to the presence of more blood and rises to the point where it can cause damage to your retina. It was thanks to the experiment with Scott Kelly that NASA discovered that it is the puffy face and bird leg syndrome that causes the vision loss affecting many astronauts. During his year in space, Scott Kelly suffered damage to his retina and optic nerve, which is bad news for long-duration space travel. Without a way to mitigate these effects, there is a real possibility that multi-year space travel could leave an astronaut blind. Not all astronauts suffer from vision loss, but it is a common enough experience that it needs to be mitigated by some external measure. The best scenario would probably be some kind of artificial gravity, which unfortunately is something that won't happen soon. There is also the proposal of rubber suits to help push the blood back to the legs, but these suits are not usually comfortable to wear. The reality is that no one knows yet how to solve the puffy face and bird leg syndrome and the possible vision loss associated with it. And until very recently, eye damage was the main concern for travel to Mars. But that has just changed. A new article published in the journal Nature conducted the first study on how staying on the space station affects human organs, particularly the kidneys. It was already a known fact that the chance of kidney stones increases when we are in space. This is a consequence of the kidneys processing all the calcium lost from the bones. The new study indicated that the consequences for the kidneys are even worse. During their stay in space, their very physiological structure seems to be damaged. The kidneys lose their ability to function. So far, in humans, the damage had not been severe. But experiments in rats indicate that kidney damage can progress to the total loss of organ functionality. The main cause of kidney damage is likely the lack of gravity, but radiation damage can worsen the situation and accelerate the loss of kidney function. And this is quite unpleasant news for long-duration space travel. According to Dr. Kate Sewell, one of the study's authors, if we do not develop new methods to protect the kidneys, I would say that an astronaut who managed to reach Mars would need dialysis on the way back. And this is quite problematic. After a year in space, Scott Kelly returned to Earth. Your muscles and bones are weaker, and your blood tests indicate the presence of inflammation. The inflammation peaked shortly after landing on the planet. Perhaps the brutal journey back home causes inflammation. Or perhaps the body, unaccustomed to gravity, interprets the weight of the surface as harmful and initiates inflammatory processes. In any case, Scott Kelly spent weeks feeling as if he had a severe and debilitating flu before he began to recover from his journey. The duration of his journey is similar to the time needed to go to Mars. If Scott Kelly's mission were to Mars, everything I described in this video would only be the one-way trip. It would be at this moment, with high levels of inflammation after having battled bone, muscle, weight, and vision loss and radiation damage, that the real mission would begin. The distance to Mars is enormous, and not just in spatial terms. We still need to greatly increase our knowledge about the human body in space before it is safe to send a human to Mars. The good news is that this will not be in vain. The physiological challenges an astronaut faces in space have analogues on Earth, such as aging or problems associated with being bedridden or immobile for long periods. Many of the proposed solutions for the puffy face syndrome are based on treatments to minimize negative effects in bedridden people on Earth. Helping astronauts to be healthier in space will help humans live better here on Earth too. Space is the future of humanity, and not only in technology, but also in health. And knowing all this, would you spend a year in space? Type it for me here in the comments. Thank you very much and see you next time.